Hi everyone, so in this video we're looking at voltage current graphs and Ohm's law, how voltage and current vary with each other as you increase the potential difference or the voltage through different devices. It's a really important part of all specifications. You need to know what these graphs look like, in particular, the shapes of them and why they are those shapes. So we'll be exploring those graphs. Three key components: an ohmic resistor, which is one that follows Ohm's law, filament lamp, and a diode. You need to understand what these graphs tell you about the resistance and the current flow as you change the potential difference. And we'll also, whilst we look at those graphs, we'll also reinforce the idea of direct proportionality, which we looked at in a previous video. And quite a small but subtle point, but one that people miss or misunderstand quite often, is the difference between Ohm's law and V equals IR. They are not quite the same thing. As we'll see, they are related in some ways, particularly for ohmic materials, but they are not the same thing. So this is a setup, an experimental setup you need to be completely familiar with. What you're going to be doing, we're going to be varying a voltage, a potential difference, across a component. In this case, we're looking at a lamp. And we're going to see how the potential difference varies with the current, as I've said lots of times now. To measure the potential difference across that lamp or that device, whatever that device might be, we're going to use a voltmeter. That needs to be in parallel across the lamp. Voltmeters are always in parallel across the lamp, across the device. And the ammeter is going to measure the current, and that needs to be in series, so in the same loop as the device you're measuring. You will probably get 2 or 3 marks for that, to be honest, just by putting the ammeter in the right place, by putting the voltmeter in the right place, putting the device in the correct place as well. You will need a potential difference source, a power supply, but you will also need to vary that. And there's usually a mark for saying how you might vary it. You might get away with just saying a varying potential difference, but often you would need to add this device here, which is a variable resistor. By changing the resistance through of the circuit in itself, you're going to change the potential difference across the device you're measuring. You'll also, for reasons which I'll talk about shortly, want to have a switch in there. Again, not always a mark, but I think it's really useful to have a switch in there. As I say, you're going to need to know that off by heart. So you need to know that setup. 3 or 4 marks. Just make sure you understand and know it. So the method, you're going to connect the circuit with a power pack or a voltage, maybe batteries. You could just add those batteries one by one. That would be a way of changing the voltage as well. You're going to measure the voltage across the bulb or the device that we're talking about. You're going to increase the voltage. You're going to add a battery, or you're going to turn the knob on the power supply, increase it to 4 volts, or you might just change the variable resistor. Yeah, whatever happens, you're going to see a change in this voltage. And hopefully you will also, or you should also see a change in the current. And then you'll put those readings into a table. So things to really remember to make sure you're getting the marks for this. You need to make sure your ammeter is in series. You need to make sure your voltmeter is in parallel across the component that you're measuring. And then to improve the accuracy, I mentioned that switch. I always think it's worth putting it in. One of the things that we'll see is that for any component, the resistance will change. That will affect your results if the temperature increases or the temperature decreases. Every time you have a current flowing through a wire, it's going to cause heating. And so what you want to do is to reduce that heating there so you're not affecting your results. So between each reading, I always suggest it's a good idea to open the switch so that everything is cooling down. When you want to take your readings, you close it, take your readings, and then reopen it. You don't want the whole setup to be getting hotter. This is the table, as I said, that you would have. Notice you've got some positive voltages, you've got some negative voltages. I'll talk about that in a second, but all you would do is fill this table in. I would suggest that very quickly you jot that down, and I'm going to show you a bit of software that you can use, or online demonstration that you can use to have a go at this. So I may well have talked about this before, or you've heard me talk about it in a previous video. This is called PhET. It's just an online platform, incredibly useful, totally free. PhET, just put it into Google, PhET, electric circuits. There's lots of demonstrations, but the electric circuits is particularly good. And you can set up, takes a bit of playing around with, but once you've got used to it, it's really easy to use. And you can literally, what I've done here is set up the circuit that I showed you there. You can change the settings so that they're not exactly as you would want for GCSE, but more like schematic, with the symbols for the cell. The resistor is slightly different to how we normally would want it in GCSE. I usually keep it like this because it looks like what you would have in a lab itself. I've got my switch here, which I can open, so there's no current flowing. And you can see what I've got here is a resistor, which I can change the resistance of. I've got my ammeter in series. I've got my, in this case, a resistor. I'm going to see how the voltage varies across the resistance, okay, across the resistor. But I could change that. Let me just quickly show you how I could do that. Just delete that there, and I could put in a light bulb instead if it's going to let me. I think I need to just shift that over. Okay, so now I can see that. I can close my switch. Right, the point is that I can then change this resistance. Don't worry about the resistance of that. That's not something you need to plot, but you'll see there that that is changing the current and the voltage. Okay, so that's effectively what you would have on your power pack. Yeah, that would be effectively the knob. Inside the power pack, there was just a variable resistor, changing how much potential difference is available for this lamp. And I would just plot. I start with maybe that. What we got there, I can't quite see my voltage there. I can change the voltage of my battery. You could just change the battery voltage directly. I would really have a play with that. The end result is that you can fill in this table. I promised that I would show you what these negatives mean, because that sometimes confuses people. So in the lab, when people are doing this in school, people often get very, very upset when these potential differences in these currents come out as negative results. It's nothing to worry about. All you need to worry about is the actual value. If you do want to change it, you should be able to switch round this battery. So if I turn that battery around, I've now got a negative voltage. I should have a negative current as well. I'm not sure why that hasn't come out negative, but very easy to switch that around, and don't worry about that. So once I've got my table, and if you were to do that with a fixed resistor, make sure you don't change the resistance of that resistor, you could plot those results, and what you should get is a straight line. Not just a straight line, it's a straight line that goes through the origin. And you should be aware that any straight line that goes through the origin is called directly proportional. So a straight line graph passing through the origin shows that the potential difference is directly proportional to the current, or the current is directly proportional to the potential difference. If I reversed, as I said, if I reversed that voltage, so if I turned the battery around, I'd get negative voltages and I'd get negative currents. It's exactly the same shape on the other side of that graph. The constant gradient indicates that the resistance is constant. So for a fixed resistor, as the name suggests, we would hope that a resistance would be fixed. A wire, to a certain extent, it will be fixed, but as we'll see in a second, it does change as that wire heats up. And what that's showing you is that as we increase the voltage, remember the voltage is kind of, we can think of it like the push, okay? As we increase the push by the battery, the force through which those electrons are being pushed, the current is increasing, yeah? If you try and force a fluid or air through a straw and you blow on it softly, you're going to get a small current. If you push on it harder, you blow harder, you're going to get more current. So that is going to be directly proportional, and that is going to give us the resistance. But if I were to use a higher resistance, what's happening here? I need to think about this quite carefully. In this case, if I were to increase, or if I was to produce the same voltage, okay, for the first one we had a voltage and there was quite a high current. With this one, with a lower gradient line, I'm giving it the same potential difference, but I'm getting a lower current. So I'm blowing my straw effectively with the same voltage, but I'm not getting so much air flowing through it, or not getting so much electric current flowing through it. Well, what would be the reason for that? It must be that there is some resistance slowing down that airflow or slowing down that electric current. And so that would suggest that the resistance is greater. So the lower the gradient here would suggest that it has a higher resistance. Similarly, if I have a steeper graph, a greater gradient, I'm getting, for the same voltage, I'm pushing with the same amount, but I'm getting a greater current. It's flowing more easily. And so this steeper graph is going to suggest that it's a lower resistance, kind of the opposite of what you might expect. The greater the resistance, the lower resistance. Little caveat though, you do need to be careful. Sometimes the examiners are sneaky. Usually you would plot this as a V graph on the VI graph with the voltage on the x-axis and the current on the y-axis. And that's going to tell you that as they get steeper, the resistance is lower. But don't just learn that off by heart. If you can at all really get to the deep understanding of it, if they for some reason switch these around, you're going to have the opposite idea. So you really want to think, if the potential difference, that push is increasing, but the current is going down, then that means the resistance is going to be greater. So just think about what these gradients mean rather than just learning it off by heart. But as I say, they normally have it with the voltage on the x-axis and the current on the y-axis. So in this case, this wire or this resistor obeys Ohm's law. Okay, what Ohm's law states, and this is a definition you do need to know, it's in the green, make sure you write this down, make sure you learn it. The current is directly proportional to the voltage for a resistor at a constant temperature. That is Ohm's law. Okay, it is not quite the same as saying that V equals IR. In this particular case, things that do follow Ohm's law, it's always going to be the case that V equals IR. So I could take a voltage, let's say that was 3 volts, and I had a current of 1 amp. Then I could use V equals IR, and I could work out that R is V over I. I could work out that it's 3 over 1, which is 3 ohms. And that's true. That's always going to be the case. As we'll see in a second, when things do not follow Ohm's law, when they are not producing a straight line, direct proportionality, a straight line going through the origin, it doesn't mean that V equals IR is not true. Okay, so just because something doesn't follow Ohm's law, it doesn't mean that V equals IR is not true. That is always the case. That is a relationship, that is a calculation you can always do, but it's not the same as saying, it's not the same as a description of Ohm's law. Okay, Ohm's law is only true of an ohmic conductor at a constant temperature. An ohmic conductor meaning that it follows Ohm's law. Okay, so if you go back to the FET now, you could have a go playing with a diode. You could find that component. You could have a go at a filament lamp. And I'm just going to show you what the graphs you would expect to find are. In this case, you can see for a filament lamp that as the voltage increases, the current is increasing. It's fairly proportional, directly proportional to start with, fairly straight line. But then as the voltage continues to increase, the current is still increasing, but it's increasing at a lower rate. Now don't forget that if you wanted to know the resistance at a given point, at any given point, you could use V equals IR for those numbers at that point. What you can't do is the gradient, which sometimes we talk about. Okay, you need to use the V equals IR for a given point. But hopefully you see here that as the voltage increases, the current is still increasing, but it's not increasing at the same rate. So it's increasing its resistance. Its resistance is getting greater, so it's harder for that current to increase. And again, the shape of it is exactly the same, but in the opposite quadrant when you go negative. Now, why is that the case? Well, the resistance of the filament lamp increases as the temperature of the filament lamp increases. That's how a lamp works. Yeah, a filament lamp, an old-fashioned lamp, it works by way of resistance increasing, and as a result, it gets hotter. We'll look at what that entails in a second. But the key point there, a lamp does not obey Ohm's law. Yeah, it's not a straight line. It's not directly proportional. It does not obey Ohm's law. So why does that lamp get hotter? Well, you imagine these electrons which are moving in all directions, and you've got your ions which are fixed in a lattice. It's the electron flow. Okay, they're moving in all directions, but they're slowly moving through that wire. Now, each time they bash into an ion, they're going to transfer energy, and that energy is going to be transferred in the form of heat. So as it goes through this filament, those electrons are transferring heat and they are giving out heat. As a result of that, what's going to happen to these ions? Well, they're going to vibrate more. They're going to vibrate. Remember, in the lattice, they are vibrating, but they're fixed in position. They're solid, they're metallic lattice, so they're fixed positions, but they're vibrating. But if they're given more energy, then they're going to vibrate more, and as a result, the chance of these electrons bumping into them is going to increase. And therefore the electrons are going to transfer more energy. So they're going to get hotter. So it's like an escalation. As that energy increases, the vibrations will increase more, and so it gets hotter and hotter. Therefore, in effect, what's happening is the resistance is increasing. It's harder for these electrons to work through that metal. I always talk about going through a classroom or just a hall anywhere, a playground. If you've got everyone standing still, it's easy to walk through that playground. If everyone's moving around crazily, you're potentially going to bump into people, and each time you do that, you're going to lose some energy, and that's going to be given out as heat. Okay, so here's an example where you've got something quite extreme. You've got a high current here, and that is able to melt or certainly make something red hot, a bolt or something, because you've got a very high current. Okay, the third component you need to look at is the diode. Really useful component, but for GCSE, all you really need to know about it is that it has this shape graph. You can again play around with it on the FET there, plot that graph, and this is what it's going to look like. As you increase your voltage, there's going to be no current. And then suddenly, at a particular voltage, the current is going to shoot up. In other words, without a particular push, without a large enough push in one direction, no current will flow. In other words, the resistance is effectively infinite. Okay, it's basically an insulator. But once that voltage reaches a certain point, the current is able to flow. If you reverse that battery and you gave it some negative voltage, however large that voltage is, or that potential difference is, you're never going to get a current. In other words, the current in a diode only flows in one direction. And it's got this symbol showing you that the current only flows in that direction, the direction of that arrow. So current only flows in one direction, shown by the arrow on the symbol. The diode has a very high resistance in the opposite direction. Light emitting diodes, which is the form that you often see and are really often used now in light bulbs and things, they are just diodes, but they give out light, and they look like those things. You might have seen those in school. And the symbol is slightly different. You have these arrows here indicating that light is given off. Okay, the final two things we're going to look at here are thermistors and light-dependent resistors, LDRs. So for these, you can't demonstrate this on the FET, but you actually need to be in a lab to do this, and you would see how the resistance actually changes with temperature. So another practical you could do would be measuring the resistance as the temperature of maybe a liquid changes. For thermistors, you need to be aware that as the temperature increases, the resistance decreases, the opposite of what you might say for a wire or for a lamp. As the temperature increases, the resistance decreases. And so you would get something like that. If it's hot, you're going to get quite a low resistance with a high gradient. And if it's cold, you're going to get a lower gradient, meaning that it is a greater resistance. LDR, light-dependent resistors, the same idea, but this time rather than temperature, you're talking about light intensity. So when there's more light, the resistance decreases. When there's less light, the resistance increases. So very similar. The graphs are very similar. Okay, have a little go at these. There's some words for you. See if you can just fill in those gaps. Pause the video and I'll give you the answers in a second. So the resistance of a lamp increases when a lamp comes on and the filament rises in temperature. That's why the resistance increases. A diode only allows electric current to flow in one direction. The allowed direction is shown by the arrow on its circuit symbol. The resistance of a thermistor decreases if the temperature is increased, and the resistance of an LDR decreases if the light intensity is increased. Okay, so what have we learned today? You should be able to describe and explain the experimental setup used to determine how current varies with voltage through any component. Describe and explain the different graphs for ohmic resistor, a filament lamp, a diode. Explain how resistance in components is affected by a change in temperature, and explain how resistance of an LDR and a thermistor is affected by light intensity. Okay, I hope you found that useful. Look forward to seeing you in the next video. In the next video, we'll be looking at series and parallel circuits.